Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. This is for the applied electronics students. As students of electronics who are studying the subject on physics of materials. Materials means what? You are semiconducting materials. Now, in this lecture 2, we will have band theory of solids. Now, the semiconductor people or the electronics people who are dealing with semiconducting elements and semiconducting compounds, which give rise to transistors and very many electronic equipments, they have to have a very good knowledge on this particular subject, namely band theory of solids, because this alone gives you about the conductivity that is taking place in semiconductors. Now, the contents of this lecture or a review of free electron theory, the Somerfield's model of a metal, that is again the so called quantum free electron theory. Now, so far we have seen how the electrons in metals were treated by Drude and Lorentz, which is known as the classical free electron theory, because they considered electrons as gas molecules. But as I told you in the last lecture, electrons are not classical objects. They are quantum mechanical objects. They got a spin. You know, you do not have spin for a ball. Maybe you can talk of the spin for a cricket ball, but anyway, the spin is a quantum mechanical concept. So, therefore, electrons being quantum mechanical objects, you have to introduce the quantum mechanical concepts for the electrons. So, it was given to Sommerfeld. The credit goes to Sommerfeld. Now, before we pass on to Somerfeld's free electron theory, whatever Drude got, I will show the expression from what we got from Drude's theory for the electrical conductivity sigma. It is given in terms of N, E and mu. So, you write sigma is equal to N, E, mu. This should be remembered always, because whatever that I am giving here, which is applicable for metals, it will be extended to semiconductors, right. You will have two terms in one term, two similar terms. Here n refers to the number of free electrons available per unit volume, E is obviously the charge, and mu stands for the so called mobility, right. Mobility is what? It is E tau by m, and tau is the relaxation time, how far the electron is free, that is the time taken between two successive collisions, and you got a parameter here. It is the speed of the electrons, V f here, the speed of the electrons, the average speed, and lambda is the mean free path, about which I told you. I showed the picture in the earlier lecture. And we will now move on to a fundamental problem. It is, even though it is fundamental, it has got great significance. The problem is the particle in a box. What is meant by a particle in a box? Some teachers come to the classes with a box containing chalk pieces. It is also an example for a particle in a box. The chalk pieces cannot come out of the box of their own, right. And you have got water in a well. The water of its own will not come out, right. You have to give some energy to take the water out. What is the potential that governs the water or the chalk piece? It is the gravitation potential. The chalk piece in the box will not be able to come out of its own, right, because the chalk pieces are held within the box by the gravitation potential. And similarly, the water in a well is a classical well. Water in a well, water will not come out of its own. You have to give some energy. Now, similarly, electrons in atoms, electrons will not come out from the atom, and the electron in a molecule or electrons in solids, these are the examples for the particle in a box. Electrons in semiconductors are again examples of a particle in a box. So, the problem may look to be very trivial, but it carries so much significance, because it is going to give rise to an expression for the density of states. I will tell you about density of states later, but in this picture what you observe now is you have a box here, right. You have got a box. What is the length of the box? The length of the box is L. From the box goes from x equal to 0 to x is equal to L. This is the box, right. Something like a box which contains chalk pieces. So, you have got a box here, and you have got an electron inside the box, and the potential energy of the electron here inside the box is 0, whereas if the electron comes to the edge, you have got a box here, right. This is a box, and what happens to potential? It goes to infinity, right. It goes to infinity, and similarly here also it goes to infinity. So, outside the box the potential energy is infinity. Can you find the electron here or here outside the box? If you have the electron outside the box, or even at these 2 points where the potential energy goes to infinity, whether you can allow a particle to have infinite energy? Can you have infinite energy for a galaxy, or whether the energy of the sun is infinity or the energy of the galaxy will be infinity? Infinity can be found only in mathematics. No physical system can have the energy or momentum as infinity. That means the electron should not be found in this region as well as in this region. The electron cannot be found here. If the electron is found here, the energy becomes infinity, right. The potential energy becomes infinity, means what about the total energy? Total energy is nothing but kinetic energy plus potential energy. If the potential energy goes to infinity, infinity plus something, anything is infinity, right. Whatever be the kinetic energy, if the potential energy is infinity, the total energy will become infinity. But any realistic particle, it may be an electron, may be some other particle, or a nucleon in a nucleus. In a nucleus you have got nucleons, the nucleons in a nucleus, again it cannot have infinite energy. So, what are the examples of particle in the box? I told you about the box. Water in a well, it is a classical well. Now, I am talking about a box, means the electrons held by electrostatic potential. What holds the electron to be inside the atom? It is electrostatic, the Coulombic force, the Coulombic potential. It makes the electron to be bound to an atom or bound to a molecule or bound to a metal or a semiconductor. What holds the nucleons to be inside the nucleus? It is the nuclear force or the nuclear potential. And so, we are talking about a potential well, and this potential is not a classical well, it is a quantum mechanical well, right. The force is again, as I told you, instead of gravitational force, you have got either a electrostatic force which is of importance to us, but for nucleons you go to nuclear physics, the force or the potential is a nuclear potential. So, I will go to the examples. What do you mean by a particle in a box? A particle in a box refers to an electron bound to an atom or bound to a molecule or bound to a metal or bound to a semiconductor, or a nucleon bound to a nucleus. All these problems, bound state problems, are referred to as a particle in a box. We are concerned about semiconductors, what happens to electrons. Our principal aim is to describe the electronic energy states in a semiconductor, right. We are trying to understand how electrons behave in a metal, right. Somerfeld gave a theory, it is called Somerfeld's free electron theory of metals. So, he was not knowing about semiconductors and so on. So, he gave the theory only for electrons and metals. So, we are discussing a metal, right, how electrons, how do you visualize electrons in a metal. Okay. Now, the visualization is as follows. As I told you in the previous lecture, you take a sodium metal, you have got 100 sodium atoms, and you want to explain conductivity of sodium metal. How will you have conductivity? You should have free electrons. The valence electrons become the free electrons, and what remains? If the valence electron is lost, then what remains will be the ions. That is what is shown in this diagram. You got ions here, a collection of ions, and embedded in a sea of electrons. It is called the free electron gas. You got a gas, the free electron gas. Drude also talked about free electron gas, but that gas is something like ordinary gas, but this is a gas in which we have to deal with the electrons. Even though you call it a gas, you have to treat it quantum mechanically. So, what is the basic most fundamental equation in quantum mechanics? In classical mechanics, the most fundamental equation is F is equal to ma, which is given by Newton. So, a similar equation, the analogous equation in quantum mechanics is the Schrodinger equation. So, you have to make use of the Schrodinger equation for this problem. So, you pass on to the Schrodinger's equation. So, we are talking about a one dimensional box, electron in a one dimensional box, right, a one dimensional metal. For a one dimensional metal, you write the equation d square psi by dx square plus 2m by h bar square E into psi is equal to 0. Now, in reality you should have E minus V. What about the potential? I showed you here the potential is made to become equal to 0, right. So, in the theory given by Somerfeld, irrespective of the place where you find the electron, now if you have got electron here separated by a distance r, the potential energy will be E square by r, right. So, but instead of taking E square by r will change, right, when you got electron here and electron here and electron here, when the distance changes, the potential will change. But for the sake of simplicity, what Somerfeld did was to consider the electron to move in a constant potential. Irrespective of the position of the electron, he averaged out the potential and made the potential to be a constant, because the problem is a complicated problem in reality. So, he made the potential to be constant, and finally, because the constant can be taken finally, right, it is a constant that can be added or subtracted finally. And so, what you do is the constant potential is made to be equal to 0. That is the reason why I omitted this 0 here. In reality, you should have E minus V into psi is equal to 0, right. So, we have got rid of V, okay. That is what you are having. Now, what about the energy eigenvalues? For the problem, what do energy eigenvalues means? The energies the electrons can assume, they will be given by h bar square k square by 2 m. They are the energy eigenvalues, right. You know very well that the energy will be, this is 2 m by h bar square E psi, you know, this will become equal to k square, right. D square psi by dx square plus k square psi will be equal to 0. So, the energy will be E k will be h bar square k square by 2 m. The electrons moving in a metal, we are dealing essentially with the Somerfield's free electron theory of metals, and we have to solve the Schrodinger equation like this. We have got an equation of this kind. Now, as I told you, this whole thing 2 m E by h bar square can be replaced by k square, where k is the wave vector. If you do so, your energy eigenvalues will be h bar square k square by 2 m. They are the possible energies which can be assumed by the electrons in a metal. The energy eigenfunctions will be psi k x is equal to exponential of I k x. Obviously, when you have an equation d square psi by dx square plus k square psi is equal to 0, obviously, the solution will be, you can have a sin k x or b cos k x and or a linear combination of these two, or in other words, you can have e power I k x, right, that is the solution for the differential equation. So, I have written the e power I k x as the solution. This solution is called a plane wave. It is called a plane wave because you have a sin k x or cos k x as the solution, a sine function or a cos function shifted by a phase difference. So, they are the plane waves. So, the energy eigenvalues are important. The energy eigenvalues means what? The energies which can be assumed by the electrons in solids. What about the energies which can be assumed by electrons in atoms? You go back to Bohr's atom model, wherein you find what is the energy of the electron in hydrogen atom. For the electron in hydrogen atom, the energy will be 13.6 divided by n square. So, the question that you ask is, when the electron is in the n is equal to 1 state, k shell, what is the energy? It is 13.6 eV. L shell, it will be 13.6 divided by 2 square. So, n is the quantum number which should be used for describing or for calculating the energy of the electron in the atom. But now, the electrons are not revolving. In atom, the electrons are revolving. But what about the electrons in metals? They have to carry the current. They will be going in random directions when you do not apply the field, and when you apply the field, they have to go in a particular direction, right. So, they are not attached to any particular atom, right. So, when they are not revolving, n does not have any meaning, right. N is a bad quantum number, n does not have any meaning. So, the energy of the electron will be given only in terms of what is variable here. Can you vary the mass? Mass of the electron is fixed, measured by the famous Thomson, who discovered the electron. J. Thomson is the man who measured the mass of the electron. H bar is the Planck's constant given by the famous Max Planck, that is a constant. So, you cannot play with the Planck's constant and the mass of the electron, they are constants. The only variable is k. K begins to act like a quantum number, that is very important. K begins to act like a quantum number. What is the dimension of k? The wave vector k is 2 pi by lambda. Where do you find lambda? Lambda is the denominator. What is the dimension of k? K will be centimeter inverse or angstrom inverse. So, you have to think of a reciprocal space about which I discussed at length in the previous lectures, okay, when I was talking to you about the lattice vibrations with respect to specific heat. Also I mentioned about the Brillouin zone or the reciprocal space and so on, a space in which the length will be instead of centimeter angstrom, it is inverse centimeter or inverse angstrom. That is the reason why it is called the reciprocal space. Okay. But anyway, before we pass on to the reciprocal space, what is the shape of the graph? You have got E k as a function of your k here. E k is equal to h bar square k square by 2 m. It will give rise to a parabola. It is a well known famous Somerfield's free electron parabola. What do you understand by this? Now, if you have an electron here with this k value, what do you mean you saying that with this k value? You multiply this k by h bar k, that is the momentum. What is p? P is equal to h bar k, right? P is h bar k, that is the nothing but the de Broglie equation, right? When you write p h bar k, what is the meaning? It is the de Broglie relation, right? So, when k takes a value here, the energy is this much. When k takes a value like this, the energy will be like this. So, the energy states will be discrete. The momentum will take only discrete values. You know, in quantum mechanics, all the observables. What do you mean observable? The measurable quantities. Momentum can be measured, velocity obviously can be measured, then the energy can be measured. All the measured quantities are called observables. So, according to the rules of quantum mechanics, when you use the Schrodinger equation, when you talk of energy, energy is quantized. Okay? The momentum is quantized. So, k will have only finite values. Even though you got a continuous line, the distance, the separation between two k points will be, two adjacent k points will be extremely small. That is the reason why you have continuous line. But so, the question that you ask is, if an electron is found here with this momentum, what is momentum? H bar k. With this momentum, the energy is this much. Okay? The energy is this much. If you got electron here with this momentum, the energy will be like this, right? With this momentum, the energy will be like this. Okay? Now, what about your k? K is what is the dimension of k? It is 2 pi by lambda. It is the lambda comes the denominator, and the dimension of k will be angstrom inverse. So, you should be concerned about the reciprocal space. That is what I am showing here. We talked about lattices. By now, you know, a semiconductor is crystallizing, silicon is crystallizing in a particular lattice. What is the lattice? The FCC lattice, right? The FCC lattice, two interlocking FCC lattices gives rise to the diamond structure. The silicon is crystallized in diamond structure. So, you know about the direct lattice. Similarly, now we talk about the reciprocal lattice. We have the following rules. Okay? The rules are, if A1, A2, A3 are the primitive translation vectors in direct lattice. In the direct lattice, you got lattice points. As I told you, you got in the first chapter you would have studied about crystal structure, lattice and so on. In the direct lattice, A1, A2, A3 are the translation vectors. Then you can generate B1, B2, B3. They are the primitive translation vectors in the reciprocal lattice. Okay. B1, B2, B3 are given by the cyclic relations, right. So, if B1, B2, B3 are the primitive translation vectors, then you take any point here, okay, you generate, you translate this is B1, then you B1, 2B1, 3B1, you translate the lattice points. You have to use the translation vectors B1, B2, B3 and generate what is called the reciprocal lattice. The same way as you have done in the direct space, you do it in the reciprocal space, that is shown here. The unit cell that you have got in reciprocal space is called the Brillouin zone, or it is called the in direct lattice, what you do, if you do like this, it is called a Wigner-Seitz cell. If you do the same thing in the reciprocal space, it is called a Brillouin zone, right. By now, those things should be known to you. This is a Brillouin zone for a square lattice. This is a Brillouin zone for a hexagonal lattice. You see a hexagon here, right. So, for hexagonal lattice solids, for solids crystallizing in the HCP lattice like magnesium, the HCP lattice, the Brillouin zone will be looking like this. The Brillouin zones are important because you choose some point, then you ask what is the energy. If the electron is found at this point, what is the energy, right. This is the lattice, the reciprocal lattice here. Then you have got this is the reciprocal lattice, the direct lattice here, the reciprocal lattice here. Then you construct the perpendicular bisectors and you know how to construct the Brillouin zone. The Brillouin zone for a square lattice, the Brillouin zone for the reciprocal lattice, and the Brillouin zones are important, as I told you, because of the fact that okay, for a given k, you ask the energy possessed by the electron. This is the a direction in the Brillouin zone. You ask the question, the electron is found here for a given k, what is the energy? So, you ask the question here, if you have the electron is found here, what is the energy? If the electron is found somewhere here, what is the energy? Okay. So, they are the questions that have to be raised in the case of for electrons in solids. So, Brillouin zone, as I told you repeatedly, is a very important concept when you want to describe the energy of electrons, phonons and magnons. They play a very important role. Energy will be given in terms of k, the dispersion relations, the energy momentum relations, right. Then we try to review again the free electron theory. The Schrodinger equation applied to the particle in a box problem. This is what I told you earlier. Now, the eigenvalues for a particle in a box, the eigenvalues will be n square h bar square pi square by 2 ml square, and the energy eigenfunctions will be, you can write a sin n pi by L into x. Okay. And you know, when you have got the energy eigenvalues as n square h bar square pi square by 2 ml square, this is for a one dimensional box, right. The Schrodinger equation applied to a particle in a one dimensional box, because you find x here, right. For 3 dimensional box, what should the first term, what will happen to the first term? It will become del square psi, that is d square psi by dx square plus d square psi by dy square plus d square psi by dz square. Then you will have 2m by h bar square into E minus V. V will be is taken as 0 for the sake of convenience. If you take V is equal to 0, V will vanish, E into psi will be equal to 0. The eigenvalues are given as n square h bar square pi square by 2 ml square. L is the length of the box, and in the one dimensional case you will have n square. You have got n. N is will take the positive integral values. How do you say that you should take positive integral values? Because the boundary conditions demand, what are the boundary conditions applied to the problem of a particle in a box? The boundary conditions are, when the electron is found here, can you find the electron here? Can you find the electron at the end points? If you have the electron here, what will happen to the energy? The potential energy will go to infinity. Can I allow the potential energy to go to infinity? If the potential energy goes to infinity, the total energy will go to infinity. So, you should not allow the electron to be found here. So, what are the boundary conditions? When x is equal to L at the end points of the box, the one dimensional box or the 3 dimensional box, right. At the end points, the probability of finding the electron should become 0. What do you mean by probability? Psi square should become equal to 0 or psi should be equal to 0. So, the boundary conditions are at this point x equal to L, at the end point psi should be equal to 0, and similarly at x equal to 0 also psi should be equal to 0. In all quantum mechanical problems, the boundary conditions alone will give the eigenvalues. The eigenvalues, they come invariably through the boundary conditions. So, the boundary conditions are important. By using the boundary conditions, you come to the case, namely the you have the energy eigenvalues in this fashion. For a 3-dimensional box, there will be n will be replaced by nx square plus ny square plus nz square. Okay. We will deal with the things in detail in the lectures to come. Let me now summarize as to what we have learned from this lecture. I told you that Drude attributed the basic postulates, basic ideas which are used for the gas molecules. The electrons are treated like gas molecules, but electrons in reality are not gas molecules. So, the credit of using quantum theory or quantum mechanics to electrons are quantum mechanical objects. For the microscopic particles, you have to make use of quantum mechanics. So, the credit goes to Sommerfeld. Sommerfeld was the first to introduce the quantum concepts to the electrons in a metal. He did not consider the electrons like gas molecules as was done by Drude. So, he indeed was the first person to introduce the quantum concepts to the electrons in metals. Sommerfeld considered electrons to move in a constant potential and arrived at their energy eigenvalues and eigenfunctions. We saw the energy eigenvalues and eigenfunctions which are obtained, and the energy of the electrons can be had from the Sommerfeld's free electron parabola. We had the Sommerfeld's, the EK curve, the Sommerfeld well known free electron parabola. Particle in a box refers to all bound state problems. Its 3-dimensional extension will give the expression for the density of states, which is a very important parameter which we will be discussing in the lectures to come. And again, the Fermi-Dirac distribution function is again a very important function which will be made use of to determine the number of electrons you can have in the conduction band or valence band. Therefore, Sommerfeld was able to obtain the expression for the Fermi energy and Fermi momentum. Now, there are some other things for the continuity sake I am talking about the Fermi energy, Fermi momentum, and some of the other things which we have to see in the lectures to come. And the questions are, how were the electrons treated by Sommerfeld? What is meant by a particle in a box? What are the energy eigenvalues and eigenfunctions for a particle in a box? What is meant by density of states? With this, we come to the end of this lecture, and the rest of the things we will see in the lectures to come. Thank you.